Hey, welcome back, you crazy cats. Today we're going to talk about a few different things. We're going to learn about the definition of momentum. We're going to differentiate between momentum and inertia and integrate momentum, force, and time into impulse. Here's some linear momentum here. Definition of linear momentum. Linear momentum of an object is the product of its mass and velocity. So we have here P is what we use for momentum. Don't ask me. I don't know why, other than it was decided a long time ago. Equals mass times the velocity. And note that momentum is a vector. It has both the magnitude and direction. So that's why we have the vector above it. SI unit of momentum is kilogram meters per second. This unit has no special name. The reason why we get that is mass is kilograms, as you can imagine, and velocity is meters per second. So when you multiply those together, that gives you your units. There is no special derived units for momentum like there is for other units of, or other quantities in like force or other ones like that. Linear momentum. For a system of objects, the total momentum is the vector sum of each. And that's what they're showing here, that the momentum, is equal to all of the individual momentums added up. So it's the sum of the momentum of all of the individual momentums. And in this case here, so they have momentum 1 is 5 kilograms. Momentum 2 is 8 kilogram meters per momentum 1 is 5 kilogram meters per second to the right. Momentum 2 is 8 kilogram meters per second to the left. And momentum 3 is 4 kilogram meters per second straight up. If you were to take 1 and 2 and add them together, you get 3 going to the left, and that's why over here they're saying the resultant, or the total momentum in the x direction, is 3 to the left. They have a total of 4 going up. So when you put those two together, we get 5 kilogram meters per second at a 53-degree angle from the horizon. The change of momentum is the difference between the momentum vectors. So as we look here, we have one object is coming in, so we have an object that's coming in, is the initial momentum, and then its momentum after it's reflected or bounced off is in this other direction. What they want you to notice here, to start off with, is that the angle that it comes in with is going to be equal to the angle that it comes out with, and that's measured from the normal. All right, notice that they are measuring that from the normal. A lot of times this would be called the incident angle, and this would be our reflected angle. When we look at this then, when we put these together and start to graph this, we say that the change in momentum is equal to P2 minus P1, which equals the change in the momentum in the x direction plus the change in the momentum in the y direction. And the change in the x is the momentum of x, the momentum of the second one in the x direction minus the momentum of x in the first direction. And this gets, they start to go through the equations. What I want you to notice, we know that the x is going to be the cosine of theta. We know that the y's are going to be the sine of theta. So, and all we're going to do is subtract the x components and subtract the y components of the momentum. So that's what they're showing here, but don't make it any more complicated than it has to be. If an object's momentum changes, a force must have acted on it. So what they're saying here then is that some net force, or MA, had to have acted on an object. And the way they're doing this is they're going to show you that MA is equal to a change in momentum. So what they do here first is they take the acceleration, they break it down to acceleration is equal to VF minus VI all over T. That's just simply taking our equation and solving it for acceleration. And VF would be just V, VI is V naught, over the change in time it takes. So then they distribute the M to both cases, so you get momentum and momentum. The final momentum minus the initial momentum. We could say that's F, and that would be I, if that makes you more comfortable. Well, this is the final momentum minus the initial momentum. Well, that's just a change in momentum. So what they're showing you here is that MA, or a net force, will cause or is equal to a change in momentum over a change in time. So what they're showing us here is Newton's second law of motion in terms of momentum. A net force is equal to the change in momentum over the change of time. All right. So let's do some simple problems with it here. All right, the product of an object's mass and its velocity. So we'll start off with momentum is mass times velocity. So in our first case, the mass is 100 and the velocity is 10 meters per second. So we would say then the momentum is equal to 1,000 kilogram meters per second. Or in the second case, second problem, we would say that the momentum is equal to the 20 kilogram dog times the speed it's going. And that would be 80 kilogram meters per second. So the 900 kilogram crocodile is lunging at its prey. It lunges 3 meters in 0.2 seconds. Find its momentum. Well, I know that the mass is 900. The velocity I don't know, but we can find its velocity because we can use our XF equation. XI, we can make that be 0. It lunges 3 meters in 0.2 seconds. So what we're going to say here then, sorry, I'm blanking out here, is its distance is 3 meters. It goes that way in 2 seconds. Find its initial velocity. Or find its velocity. Get rid of the meters. 3 divided by 2. So we have a velocity of 1.5 meters per second. It's actually its average velocity. Find its momentum. Momentum is mass, which is 900, times its average velocity here of 1.5. Now, we get momentum then is equal to, what is that, 1350 kilogram meters per second. From this, the reason I say this is average velocity is if we assume it was going 0 at the start, all right, and if we assume that the acceleration during this is constant, then we can say that the final velocity here was 3 meters per second, because we know that average is VF plus VI divided by 2. 1.5 equals 3 plus 0 divided by 2. Alright. Let's check something out here. Okay, we're now going to move on to impulse. We've kind of already introduced this concept. Impulse is the change in momentum. And what they're showing here is that impulse is equal to the average force times time. And they're going to prove this here to us by saying that impulse is a change in momentum, and that's mv minus mv, or mv final minus mv initial. And what we said originally is that force was equal to the change in momentum over the change in time. So they've just replaced force with the change in momentum over the change in time. And because we're multiplying by the change in time underneath here would have canceled out. We would no longer have the change in time. They've simply multiplied both sides by change in time. So they now have force times change in time is equal to change in momentum. Typically the force varies during the collision. Right? Notice that the force is going to change. All right, you start off with very little force, then you get a lot of force. So they're saying that the average force is right here in the middle over this time duration. In reality here, we would say that the impulse, all right, is force multiplied by time. Notice the impulse is going to be multiply force and time. Force is on the x-axis, time is on the y-axis, or sorry, vice versa. Force on the y-axis, time is on the x-axis. So impulse would be the area underneath the curve. I know some of you are hoping we never had to do that again. Actual contact times might be short. So they're giving us some contact times, milliseconds. Golf ball, 1 millisecond. Baseball, hit off a tee, 1.3. Football, 8 seconds, milliseconds. Soccer, if you have a header, it's 23 milliseconds. Impulse, when a moving object stops, its impulse depends only on its change in momentum. This can be accomplished by a large force acting over a short time or a smaller force acting for a larger time. So, in this case here, they have this person catching the ball really quickly. So the change in momentum is happening really fast. So you're going to have a large force, small time. All right. We understand this instinctively. We bend our knees when landing, a jump. A soft catch, moving hands, is less painful than a hard one, fixed hands. This is how airbags work. They slow down the collisions considerably, and why cars are built with crumple zones. So by putting in this crumple zone, they're allowing the car or the collision to last over a longer period of time. Well, if we have a long period of time, that means the person in the car is experiencing a much smaller force. And we'll try to talk about that a little bit more as we get into class with it. But let's work out an example here. Okay, I've done a little bit of the math here to get us started on this problem, but we've got this bullet that's going to be shot out of the barrel, and it has a mass of 0.2 and a final velocity of 700. If it's a bullet, then we're going to say it starts at 0. So they want us to find the acceleration of the bullet, and they give us a time, how long it takes to come out of the barrel. So what we're talking about here is finding the impulse, and then setting that impulse equal to force times time, and then solving for the force, solving for the acceleration. So let's work our way through it. The initial momentum is 0.2 times 0, or 0 kilograms meters per second. The final momentum, the bullet still has the same mass, but it's now going 700, so that gives us 140 kilogram meters per second. So let's find the change in momentum, because there's some type of force, which is what we're going to need to find acceleration, that caused that change in momentum. So PF is 140 minus the initial is 0, gives us 140 kilogram meters per second is the impulse. So now I'm going to set that equal to find that force, I'm going to say that some force times the amount of time it takes to come out of the barrel, and that's 0.01 seconds, and I just made that number up, equals the change in momentum. Well, we just found the change in momentum is 140. So from here then, to find the force, we're going to take that 140 and divide it by 0.01. And we find out then that the force is equal to 14,000 newtons. To find the acceleration, we go back into our F equals ma equation. We now know how much force was applied to the bullet, equals the mass, which is 0.2. Solve for the acceleration. So I'm going to divide by 0.2 again. And the acceleration of that bullet was 70,000 meters per second squared. Well, hey, I hope that gives you some beginning information on momentum and some beginning information on impulse. I'll catch you on the flip side.